Welcome to the deep dive. Today we're jumping right into a really clever bit of food science. It's all about replacing those unhealthy solid fats, trans fats, saturated fats, with these high-performing structured liquid oils, oleogels.
Yeah, and this deep dive is really about the, let's say, chemical architecture behind it. Our sources get into how one specific polymer, ethylcellulose EC for short, is doing some amazing things. It's tackling that age-old fat problem in processed meats, but it's also popping up in drug delivery.
And even shaking up some really fundamental ideas in meat science, right?
Exactly, ideas that have been around for, well, decades.
And the drive behind all this is pretty clear. We know saturated fats aren't great, but the sources we looked at really hammer home that trans fatty acids are arguably the worst offender.
Oh, definitely. They significantly raise the bad LDL cholesterol, and they're unique in actually lowering the good HDL cholesterol. So yeah, finding a structural fix is crucial.
So oleogels are the fix. What are they, fundamentally?
Okay, so picture this. An oleogel is basically a semi-solid. You start with a liquid oil, could be soybean, canola, flaxseed, whatever, and you trap that liquid inside a 3D network.
Like a scaffold.
Exactly like a scaffold. And that network is made by a relatively small amount, usually under 15% of a structuring agent, or gelator. The end result. You get something with the texture of solid fat, but you keep the health profile of the liquid oil.
Okay, that makes sense.
Okay.
So you get the texture you want without the problematic fats. How do scientists actually build this scaffold, create that structure?
Well, the material points to two main strategies. The first is using structured emulsions, oil in water emulsions specifically.
Right.
There's a commercial example called Kosoon. They managed to get a shortening-like texture. The clever part is how they do it using monoglycerides and really precise pH control.
And wasn't there something surprising about its composition?
Yeah, this is interesting. 30 to 40% of the final product is actually just structured water.
Huh. Using water to bulk it up and keep the fats low.
Smart. Very smart. It allows them to minimize saturated fat and eliminate trans fat entirely.
But the main focus in our sources, it seems, was on the oleogels themselves, particularly using ethylcellulose. EC. Why EC? What's special about it?
It's kind of unique. It seems to be the only polymer we know of that can gel oil using what they call the direct method.
Which means?
It's the simplest way. You literally just mix the EC powder into the liquid oil, heat the mixture up above EC's glass transition temperature, that's around 130 degrees C.
Okay, so pretty hot to soften the polymer chains.
Exactly. Let them get mobile and disperse, then you just cool it down. As it cools, the EC strands lock together again, but this time they form that network, trapping the oil. Simple as that.
Simple in concept, maybe. And the research went into detail about what makes these gels harder or softer, right?
Absolutely. They identified three key factors that control the mechanical strength. The hardness.
Okay, what's first?
First, the oil type itself. This was a bit surprising, but the hardness really depends on the fatty acid profile of the oil. Oils with more unsaturation, think flaxseed oil, which is nearly 60% linolenic acid. They produce significantly harder gels.
Wait, more unsaturated oil makes a harder gel? That feels backwards somehow.
It does feel counterintuitive, doesn't it? But the data was consistent. Flaxseed gels were much harder than soybean oil gels, which were harder than canola oil gels.
Huh. Okay, so oil type matters. What else?
Second, the polymer molecular weight. The sources talk about this in terms of viscosity, in centipoise, or CP. Think of higher CP meaning longer polymer chains.
Longer chains, more tangles.
Pretty much. And longer chains, like 100 CP EC, made much, much harder gels compared to shorter chains, like 10 CP EC. More entanglement, a denser network.
Okay, so longer EC chains and more unsaturated oils lead to the firmest gels. What of the structure itself? Did they look at it up close?
They did, using cryoscanning electron microscopy. The images show the EC forms this sort of intricate coral-like network.
Coral-like?
Yeah, surrounding these small pores filled with oil, typically around 3 to 4.5 micrometers in size. Very tiny. And they found that if you increase the EC concentration or use a more unsaturated oil, those pore sizes actually get smaller.
Which makes sense if the gel is getting harder, right? Denser structure, smaller gaps.
Exactly. It all correlates nicely. Smaller pores, harder gel.
Okay, so we understand the chemistry and the structure. Let's talk application. Where is this EC oleogel tech making a real difference in the food industry?
The big one highlighted is replacing solid animal fat in processed meats. Things like sausages, burger patties, luncheon meats.
So taking out the beef fat or pork fat and putting in an oleogel instead.
Precisely. The sources describe successfully replacing 100% of the added animal fat with these EC oleogels, often made with highly unsaturated oils like flaxseed.
Wow, 100% replacement. That's significant. Why was that so hard to do before? Couldn't they just swap in liquid vegetable oil?
People tried that, of course. But replacing solid fat directly with, say, liquid canola oil, it caused a major texture problem. The meat products became incredibly tough, really chewy.
Chewy. Why would liquid oil make it chewier?
It seems the liquid oil disperses too effectively. It creates this huge surface area, allowing the meat proteins, especially myosin, to form this really extensive, overly strong network throughout the product.
Ah, okay. The oil lets the proteins link up too much.
Right. But the EC oleogel, because it holds the oil within that structure, it prevents that extreme dispersion. It solves the chewiness problem.
Is it just about controlling where the oil goes?
It's largely about controlling the size of the fat domains. When they looked at the microstructure of meat batters,
Yeah.
with just liquid oil, you get thousands and thousands of very small oil droplets. But when they use the EC oleogel, the average size of those fat globules increased dramatically.
How much bigger?
The median size went up by over 130% compared to using the ungelled oil.
Okay, 130% bigger. And that
Right
helps
there.
the texture how?
It brings the globule size much closer to what you see in traditional products made with solid beef fat. In the control batters with beef fat, the medium globule size was around 25 micrometers. The theory is, by making the oil globules larger, the oleogel reduces the total surface area available for the meat proteins, the myosin, to coat.
Less surface area.
Means less protein absorption onto the fat, which prevents that protein network from becoming excessively strong and chewy. It mimics the effect of solid fat particles, essentially.
Okay, that makes sense. It's a physical solution to prevent a chemical network from getting too tight.
Yeah.
But that whole explanation hinges on the idea that myosin wants to coat the fat, that there's an attraction there.
And that is where things get really interesting and, frankly, challenging for meat science.
How so?
Because this leads us straight into what the sources call a major paradox. For decades, the stability of these commoditized meat products, think emulsions like sausage batter, has been explained by protein-lipid interactions.
The idea of an interfacial protein film, or IPF.
Exactly. The belief is that meat proteins preferentially bind to the surface of fat globules, forming this film that stabilizes the whole system. It's a foundational concept.
Yeah.
But when researchers actually tried to prove this direct binding using modern, really sensitive methods, they hit a wall.
What methods did they use?
Things like surface plasmon resonance, UV spectrophotometry. They took purified myosin, the key protein, and tried to see if it would bind directly to common fatty acids, like palmitic, stearic, oleic acid.
Well,
The results were pretty stark. They found, and I'm quoting here, almost no significant decreases in absorbance, which basically means
no binding.
no measurable chemical binding. They just couldn't detect that attraction between the protein and the lipid components that theory predicted.
Did they try different conditions? Maybe the protein needed to be unfolded a bit?
They did. They tried it with bovine serum albumin, another common protein, and even heated it to about 52.5 degrees C to partially denature it, thinking maybe that would expose binding sites.
Still nothing.
Still no significant measurable binding to the lipid surface.
Okay, hold on. If the proteins aren't actually chemically sticking to the fat, why do we see those protein films around fat globules in cooked sausages? You can see them under a microscope, right?
You absolutely can, and this is the core of the paradox. The sources propose a really radical alternative hypothesis.
Which is?
That the visible interfacial protein film might not be due to chemical attraction at all. It might just be an artifact of the heating process.
An artifact, meaning...
Think about heat transfer. Fat has a much lower heat capacity than water.
Right, it heats up faster.
Exactly. So during cooking, the layer of protein immediately surrounding a fat globule gets hotter, faster than the protein dispersed in the watery part of the meat batter.
Ah, so the protein right next to the fat denatures and aggregates more quickly just because it's hotter there.
That's the idea. This localized accelerated denaturation could create that visibly dense protein layer. The IPF that we've always assumed was due to some special chemical affinity for the fat.
Wow, so it's not chemistry, it's just physics, a thermal effect.
That's the provocative suggestion. It completely reframes why those structures form and what actually stabilizes the meat emulsion. A huge potential shift in understanding.
That is, yeah, that's fundamental. Okay, let's shift gears slightly. This idea of controlling structure is obviously key. How are oleogels being used outside of food, say, therapeutically?
Right. The structural properties are really useful for controlling the delivery of active compounds. Drugs, nutraceuticals, even live bacteria like probiotics.
Where are they showing the most promise?
Two main areas highlighted were topical delivery and controlled release in the gut. For topical applications, creams, ointments, oleogels have some real advantages.
Like what?
They can often dissolve drugs better than water-based systems, they feel less greasy on the skin, and crucially, because they're lipid-based, they seem to interact well with the stratum corneum, the outer skin layer.
So better skin penetration.
Potentially, yes. Enhanced penetration. They mentioned successful use in antifungal treatments, for example, delivering drugs like clotrimazole.
And there was a specific study on wound healing.
Yes, a compelling one using a rat scald burn model. They compared oleogels using things like glycerol dibionate, which is actually a food-grade fat, as the gelator against standard hydrogels.
And the oleogels performed better.
Consistently better, especially when they added medicinal plant extracts, like from Boswellia serrata. The oleogel formulation significantly reduced wound size and inflammation compared to the hydrogels.
Was there data on skin function, like hydration?
There was. By day 21, the skin treated with the oleogel had recovered to near normal hydration levels, around 50 units in their measurement. The hydrogel group lagged a bit behind, around 45 units.
Suggesting the oleogel provides a better barrier.
Exactly. That lipid structure helps restore the skin's natural barrier function, retaining moisture and aiding the healing process more effectively.
Okay, that makes sense for topical. What about internal use? You mentioned probiotics.
Right. EC oleogels look promising for delivering sensitive things like live probiotics, such as Lactobacillus reuteri, deep into the gut.
Protecting them from stomach acid.
Precisely. The oleogel structure shields the bacteria through the stomach. But the clever part is tuning the release.
How do they do that?
By adding specific hydrophilic powders, things that like water, into the oleogel matrix. These act as disintegrants. Once the oleogel reaches the less acidic, more watery environment of the lower intestine, like the ileum or colon,
The water gets in, activates the powders.
and the powders basically cause the oleogel structure to break apart, releasing the probiotic payload right where it's needed. You can tune the release kinetics quite precisely this way.
That's really elegant, using the environment to trigger the breakdown. It's amazing, really, how this one polymer, ethylcellulose, connects all these dots.
It really is.
You go from making healthier sausages by completely replacing animal fat to potentially healing burns faster to delivering probiotics effectively,
Yeah.
all stemming from its ability to structure oil. This deep dive really covered a lot of ground.
From global health challenges around dietary fat, right down to the nitty-gritty chemistry and these fundamental questions in food science.
Yeah, and let's circle back to that protein paradox for a final thought.
Absolutely, because it's profound. We've built decades of meat science, stability models, product development on the assumption that protein-lipid binding is essential, that there's a chemical attraction stabilizing these systems.
But the direct experimental evidence for that specific binding, it's proving elusive, maybe even non-existent.
Exactly. So if that visible interfacial protein film isn't chemical affinity, if it really is just a thermal artifact proteins cooking faster next to the hotter fat globules, what does that mean?
Yeah, what are the implications?
How does that fundamentally change our approach to formulating and understanding meat emulsions and perhaps even other food systems? And critically, what other phenomena across food science, things we currently explain with chemical interactions, might turn out to be driven by these simpler physical or thermal differences instead?
A huge question to ponder. Thanks for exploring that with us today, and thank you for joining this deep dive.